Hi, welcome everyone. I'm Ardon Toonstra, and I will be the moderator of this session. I will keep an eye on the Q&A section in Whova and pose the questions to Nikolai. So, Nikolai, if you're ready, you can share your screen and start your tutorial.
Yeah, let's do it. Can you see my screen?
Yes, I can.
Awesome.
Oh.
So let's start. Okay, hi everybody. So I'm glad to be on DevDays. So initially my talk was rejected, but thank you to Firely guys. 3 days ago they found the gap. So, and I'm lucky. So I have this presentation now. So let me introduce myself. I'm Nikolai Ryzhikov. I'm CTO, or usually I call myself art director of the Health Samurai team. So you see my coordinates on social media. So the Samurai it's a fire company. We have a long history with the fire. So we're crafting fire first, next generation information systems. And we're building our fire platform, which is called 8box, and plenty of open source solutions. Okay, so I want to do some announce. So we're organizing online meetups. So the next meetup is going to be dedicated to profiling. So please join us, search for the Fire Online meetup. So you see the list of speakers, deep dive into fire in the wild. Okay, so let's get to the topic. So today I want to talk about the mapping and transformation, which is really real-world interoperability challenge. For now, we have different languages, different dialects, so different formats, standards, and proprietary stuff, and our system forced to communicate with the rest of the world, which speak different languages. And we have to map or transform data in one format into another. And this is a real challenge. There is no silver bullet to solve this problem. So eventually we will get mostly fire maybe in this area, but I think even with fire, we have multiple versions and we have to map and convert between these versions. So let's talk about this topic. I prefer to have questions during the talk. So because yeah, I have a lot to say in different topics, so please stop me at any point in time and ask the question. So I would like to walk through, let's say about the general approach, that just two approaches. So you can use some general languages like JavaScript, Lua, Java, or anything else, and just write a program which transforms from one format into another. Or you can try to invent a DSL. And I would like to tell you the story how the Health Samurai invented the set of DSLs to fight against this mapping transformation challenges. So we will talk a little bit about the HL7 v2 and the smart parser. We will talk about the unidirection Jute mapping language or templating. We will talk about a couple of bidirectional DSLs. One is named BXB and another is Isomer. All of these DSLs were burned in real world when we're trying to solve the problem of information systems. Okay, so let's start from HL7 parser. Why it's important? Because in US, the essential volume of data moving around in V2 format. So this is a great source of information. And definitely we want to transform V2 to Fire because we want to develop the new stuff in Fire. And we start working with HL7 V2, this kind of archaic format, which was invented like 30 years ago from the parser. And there's a lot of heavy load on the parser. And we kind of wrote like 4 or 5 parsers during our couple of decades working in health IT. So, and we formulated these requirements with which we want to have. So first of all, there should be human readable names instead of indexes. So it should tolerate some small syntactical problems, because not all systems generate completely valid HL7 v2 messages. It would be nice if we can parse different type of messages and have a one schema. And it would be nice if we can align the naming and for the the parse result with the file naming. This will simplify in future mapping the v2 to file. Okay, so let's start from the first point. There are plenty of parsers which just split segments and give you the indexes. But our experience shows that this may bring a lot of bugs. So it would be nice to have a human readable names like this, because so there's some story. So we have a kind of reference HL7 message which were moved between our parsers, and we were thinking that this is the reference message. So we are testing our parsers against it, and when we introduced the name, we found the bug in this message. So if you think that you can remember all these indexes like PID.5 or I don't know, PV1.6, so I think it's not true. So it's better to have a names. So we decided to add the names. So we started from the amazing work which was done by Redox. They published the open source, the parser, and they did a nice job. They unifying against v2 versions. So they kind of provided universal version. And then we start giving the names. So we wrote the DSL for the parsers. So you see this DSL. Don't get into the details, but the idea that we gave the names to each field and to some components inside the v2 message. And then we did the job. So we started while we giving the names, we start looking into the fire and trying to align these names with the fire. And then we discovered the great secret. So now we know how Graham created the fire. Because if you start going through the v2 segments and trying to give it reasonable names, and the groups of segments kind of very nicely map it to the entities like resources, and you see that the basic file resources and the basic sets of the segments in v2 has a very interesting relationship. It looks like the father and the son. So I believe that it's possible to transform like half HL7 v2 to fire right on parser side. But so that's a great secret. Another problem with the parser that some systems generate not exactly syntactically valid HL7 v2 messages. So just one example. So by specification, the insurance information like in segments should go before guarantor segments. But for example, some systems interleave these segments, and formally this is not valid message, but it still has information, and this is not a big problem. But most of parsers which are doing it top down using rules, like there should go the insurance group and after that should go guarantors group, will fail on this phase. So we looked into the research space at the parsers, and we found the type of parsers which doing bottom up. So the idea of parsing bottom up, that you trying to group the tokens into the groups and then group these groups into the super groups. So you're going not from the top, reading the rules of your parser and expecting that the next segment is a, I don't know, PV1 and you starting the group encounter. But you going bottom up, you kind of grouping more and more groups, and at the end you have a message. And these bottom-up kind of parsers are much more tolerable to some small mistakes. So, and we did this bottom-up. So this is kind of unique stuff. Again, and a very interesting result when we walk through the most popular messages like ADT, ORU, and DFT, we found that we can unify the schema of the resulting parse document. So all of these messages will conform to this single schema. So this may reduce the mental load when you read and simplify the mapping, because now all of your messages are parsed into the same parse tree. So maybe some attributes may absent for specific messages and maybe some present, but it's still simplified. So you get kind of unified HL7 v2 message schema. So, and let me show how this parser works. So here we have an interactive demo. So I can load, for example, the DFT, and you see the DFT is parsed. We see the patient element, and you see the work which we done by making it fire-like. It's almost valid fire patient, maybe. So you can go into the address and stuff like this, and then you can load the ADT and again parse it again, and you will get the same parse tree. Let's just jump between ORU. So some keys are disappearing, some appearing, but still it's the same message structure. And most of these segments are shaped like fire. They're not exactly fire because there's some additional stuff, but so we are working to make it almost like fire, maybe moving some strange fields to extensions. But so like 80% may be done on the parser side. So that's the parser. So it's going to be, it's a brand new stuff. It's going to be published as a part of 8box, and probably we will open source it. So this is the parser section. And if you have questions about the parser, you may ask it now.
So far, there are no Q&As.
Yeah, so this is a small session. Yeah, you can ask because we will move forward to other topics. So I hope guys can unmute yourself and just ask the question. So not so much attendees, so we can just make it like a meetup. So if no question,
Hey, Nikolai, what versions of HL7?
Okay. Yeah, got your question. So we did the trick. So the Redux tried to create the unified version of V2. They tried to find the common denominator. If you go to the GitHub of the Redux, they have this library published. And we started from this. So we may call it the most generic version. So I understand probably in some very, how to say, if you go deeply, maybe you will find these differences, but Redux claimed that they covered most of versions with the one set of rules, and we started from there. And from our experience, we did not see any problems parsing 2.5, 2.3, even 2.7.
Oh, great. Thank you.
If you can point into some tricky segments and breaking changes, yeah, we will work on it.
Nikolai, we also received a question in the Q&A.
Yep.
How do you handle the ZZZ segment?
It's configurable. So you can extend the parser with additional meta information, which will look like this. So here you see the known segment, but you can add the configuration for the parser to semantically parse that segment. And parser will parse into some JSON stuff.
Hi, Nikolai. One question following. Yeah, I asked that one. This is a question. What's the output of the parser? Is that the JSON or?
It's a JSON. Yeah, it's a JSON. It's a JSON structure. So here it's drawn like YAML, but yeah, it can be JSON. So let's call it JSON-like output.
So how to configure like the output of the parser? Do you like the configuration or?
Sorry, can you repeat the question?
So how I can customize this parser, for example, set up the ZZZ segment or the.
Okay, yes. So the parser is completely configurable through this data DSL. So here you see the Eden format. I will in future I will tell a little bit, but it's almost JSON. Yes, you see just arrays, keys, and values, and the parser is completely configurable, and you can reconfigure this metadata to the parser, and it will parse in a different way.
Okay.
Yeah, the parser built on top of metadata, and you can change the metadata, override it, and that's how you extend the Z segments as well. Okay. Any other questions? Or move forward so we have more topics. Okay. So, and here we are. So this is a Jute DSL, domain-specific language, which was developed like 4 years ago, almost at the same time as a fire mapping language. It was presented to the Gram. So it's a unidirectional data templating. So it was inspired by XSLT transformation, when you can transform XML with XML. So the Jute is a, let's say, JSON transformation written in JSON. And we used this engine a lot in a different project to do the structured data capturing, I don't know, mapping V2, some custom integration and stuff like this. And I think there are a couple of presentations on these DevDays which are using the Jute mapping language. So let's take a look. Here we see that this is in YAML, but I hope you understand this is a JSON-like structure. So the idea that you write the result template as a data structure, and sometimes instead of putting values, you put expressions. It can be a fire path expression, or Jute support both engines, the Jute path language and the fire path language. They start with a $sign. As well, you have some special instructions, the command, keys which start with a $sign, and you can do some mapping or conditions or stuff like this. And we will see more on the demo. So, but before, let me introduce the Eden. So we are heavily metadata-driven guys. So a lot of stuff we configure with the data, like the fire do, like structure definition and stuff like this. But JSON is too limited for us. The YAML, if you go to the YAML specification, it's crazy specification. So, and we found the ideal format. All of them are JSON-like. So it's called Eden. So it's almost like a JSON. So, and I just teach you in 1 minute how to read it. So for example, in a Eden format, you have a special type which is called keyword. It's a string, it's an internalized string, and start with a colon. And it intended to be used as a keys in a maps or objects, or how you call it, I don't know, hash maps. And the commas are space symbols in Eden, so you can put any number of commas, or you can skip these commas. And there another data type which is called a symbol. It's another type of string, but it's like a name of the function or name of something. And we use this string to refer other models described in Eden. And there are comments. So I remember that Graham said that he missed the comments in JSON. So the Eden support the comments, and it has some bunch of another container data structures, for example, like a set. So unordered collection of unique values. So it's almost like JSON, so less syntax, the same meaning. It's quite irregular, and most of our DSLs, we are moving from YAML and from JSON to Eden. Okay, so, and now we can go to the Jute demo. So here I have the page. So this is a template. Okay, can you see this code? Yes, it's big enough.
For me, it is.
Yeah, so this is a template, and this is a source data. So we see it like a fire patient. So we can map, let's kind of flatten the fire resource. It may be useful if you want to render it or if you want to load it into some relational database and do analytic. So, and we put the key DOB and we put an expression which says take element birth date. And expression, let's map the names. Let's flatten the names. Like, let's take the first name given first. And let's map the last name. Here, let's put simple expression. You can definitely write more complicated expressions. So, and we see the result here. And here is an example of the instructions, special instructions. So this is kind of conditional written with data. So the 3 special keys. So the if key mean if this expression evaluates to true, then this branch will be inserted into the gender. But here we see the primitive type, but it may be a nested map or object. So, and this is how it works. So we can, and this is interactive demo. So we have a lot of such type of tooling when you work on the mapping. So for example, let's say female, we see the F here. Let's change this, and it's changed. So you can go to the Jute documentation. It has a lot of built-in instructions. It's extensible. It has a couple of engines. It's open source. It has a couple of engines. One is written in JavaScript and maybe embedded into your system if you use JavaScript or use some JavaScript interpreter. Another is written in Clojure, and you can run it in JVM. It's more performant. It's compiled. And it's built into the 8-box. So that's about the Jute mapping language, or I call it usually template language. So do you have any questions about Jute?
Yeah, Nikolai, Santosh.
Yeah.
Yeah. So here you have used on the left side is the template, and the right side you have given the Eden input, right? So if I have the fire input, how do I like transform? Do I need to transform the fire resource to Eden resource and then apply the Jute template?
It's very easy. It's just one call, like a read JSON. So because you can easily read JSON to Eden.
Okay.
But so we usually write in Eden. So usually you can just transform JSON. Yes. So as input, we use the Eden mostly for the DSLs. Yes. This part, when we describe the rules, this part is better fit with Eden because we have more types like symbols and stuff like this. So we usually write what we call data DSL with Eden, but the input may be JSON, and it's very easy to transform between the Eden and JSON. So.
Got it. Thank you. And is it open source, this Jute?
Yeah, Jute. Let's search it. Yeah. So this is a Jute written in Clojure, and their reference to the Jute JavaScript from here. Here is the specification stuff, and I think even the online demo, you can go and play with the Jute by reading documentation that's available in internet. So that's about Jute. So, and if you will have some ideas or find some bugs, you can just use GitHub to report on issues.
Thank you.
Jute and JavaScript, yeah. Okay.
Nikolai, we also had a question about the parser, still a late question, and that is if the parser also handles generation like the Redux parser.
Can you repeat it, the question again?
So the question is, does your parser also handle generation like the Redux parser?
What means generation?
I'm not sure. Perhaps Sam can explain the question better.
Okay, I think
Otherwise,
from Redux. Maybe he can join and we can discuss it at the QA session. I mean, join the Zoom meeting. Because I don't know what means generation in Redux terms. Yeah.
Okay. So then let's move on.
Yeah, sorry. Yeah, if Guy can explain what this means, I will probably answer the question. Okay, so let's move forward. And another DSL, so it's called BXB. It's not published, I think, but we have a couple of open source libraries which are built with the same ideas in mind. One is for JavaScript, which is called two-way, and another for Clojure, which is called Ironhide. And the BXB is hidden inside an 80 box, but if somebody forces us, we probably may open source, or at least I will tell about the ideas. So, okay, the problem. So sometimes we want to get the file resource, map it to some flattened representation, maybe not all of fields of the resource, then update this view, flattened view, and then get back to the file resource without losing any data. This may be used, for example, for the user interface. You flatten resource, you map these fields to the inputs on user form, and then when the guy entered the new information, you have to transform it back. So this is the idea of bidirectional mapping, that you will write the one program which will provide you the back and forth transformation instead of writing two programs which may be not consistent with each other. And definitely we are going to put a lot of constraints of bidirectional transformation, but if you fit these constraints, it may be the good solution. So, okay, so the BXB mapping is based on idea which was published, the research work language, which is called Boomerang. I don't remember the university, but you can Google Boomerang transformation. And it's based on the idea of the lens. So if to say it's simplified, so you have two functions. One is a get function which get the source and transform the source to some view representation. And another function is a put, which get the modified view and transform it to the source format. And the put operation may use the original source information to build the result. So because you may map only one or couple of fields elements from the source, and then you want to get back the whole resource. So yeah, the BXB DSL essentially written like path from, path to, and provide two functions. So one function is transform from source to destination, and another function to transform from modified destination to the source. As well, you can provide the original data which you transform. So here is how it's written in Eden. So you can read it. The first vector or array, it's a path from the source, and the second is the path to the destination. When you read this top down, when you're transforming forward, so you can read it like take data from this path from source and put data to the destination by this path. So the path supports some indexes, as well some special instructions which may, for example, filter collections by matching criteria with. So you can read this: take identifier, find the identifier with system equal to this value, and take the value and map it to the flattened field, which is called SSN, so social security number. And here you can map the value. If it's male, put the M. If it's female, put the F. So, okay. So now let's go to the demo. So that's the BXB. So how this demo works. So this is a BXB program, path to path. This is our source data we are working, and So we have only one rule, which map the birth date to the DOB. And here we see the result of the transformation, and this is a dynamically generated form for these fields. So we can, for example, flatten the names. So we see that the new input appeared for the flattened name. So that's the source, and that's the result of the transformation. And if you change it here, let's say change, and then you call the put operation, you will get the result, the resulting resource where only this stuff is modified, but the rest is keep it as it was. So let's see that the name changed, the family changed, and we map it the only first from the given, so that we keep the second of the given. So we are not losing information. We kind of patching the original data with these changes. So that's lenses. You can read the Boomerang paper about this, and you can do more complicated mapping. So here we map the gender to the sex and change and mapping the dictionary. And here, for example, we flatten this collection of identifiers to have very simple fields like security, social number, and driver license. And again, you can change, let's say DL, and then we see that only this piece is changed. For example, let's do it again. Let's comment driver license and uncomment. So let's change only SSL. Put it again. So you see that we keep the driver license as it was, and we only updated SSL. So you can read this. When you read this program backward, it says take driver license, and then go into identifier, find the identifier with the system DL, and update this value with a value from driver license. So that's how you can interpret it. So, and that's very useful approach, and we used a lot, especially for user interfaces. When you getting the resources, flatten, edit it, and then getting it back. Okay, and that's, I think, all about the BXB. So, any questions? It's a little bit harder. Okay, but I hope you feel that it's useful. So search for our open source stuff, and this is going to be part of an 8-box. So for example, yeah, you can build this simplified view, and what's nice about this view that it's updatable. So you can change this view and propagate changes back. So that's very useful. Okay, so that's BXB approach, and let's move to the unknowns. So yeah, so when we started working with the X12 EDI, so it's a huge schemas, and we want to map it to the Fire or something like Fire-like. So we come up with the idea of Isomer. Again, this is a bidirectional mapping language. So the statement like BXB, but it took different approach. I haven't seen that somebody tried this approach. So probably we will write the paper about this. But the key idea that you write in your transformation program, not about the data, not again the data like most mapping DSLs do, but you are transforming the schema. So if you have a source schema and you want to get to the destination schema, you write the set of transformation which transforms the source schema to the destination schema. And after that, we automatically build the data transformation program from the schema transformation. And we built both the forward data transformation program and the backward transformation program. And working with a schema is very interesting because you see all possible attributes. You have a validation that you map at all the elements, that you not override another existing element. So there are a lot of checks and help when you start working with a schema, with this metadata. And it's very too easy to prove that you did your transformation right. If your destination schema, which you get after the transformation, is equal to your desired destination schema. So that's very easy to prove that your transformation is completed. Okay, so this is top level view. The low level view, so the program of Isomer consists of set of operations. So this is a very limited set of operations, which guarantee that you will never lose the data and you will not have any conflicts between schemas like shadowing some attributes, I don't know, losing information. So there are kind of dozen of operations. I will show you just a couple of them. So the one very simple operation, which just rename the key. So this is a schema which has a key with some, let's say, primitive value. And the rename key, rename the key A to the key B. And this is this operation is completely reversible. It's done on schema, and it's obvious how you can generate the data transformation program for this operation. So slightly more complicated operation. Let's say you have a schema 1 and which refers schema 2 through the key A, and you have a key at schema 1, and then you can push the key to the child schema, like moving this key definition to the schema 2. There's a lot of checks that you can do this. But this is, again, this is reversible. The backward operation is a pop keys. You can move some key, like a pop attribute or element, from the child schema to the parent schema. So, and using the set of such operation, you will, your program looks like set of operation. When you run this operation top down, you transform the source schema to destination. If you run it bottom up, it will transform the destination schema to the source. So, and what's important that it uses semantic of mutation. The most of mapping stuff, you kind of using the semantic of creation something new. You're just getting data from the source and putting it to the destination. You kind of building destination from the source. And if you didn't get anything from the source and didn't put it to the destination, it just missed. So with the Isomer, there is no source and destination. Each operation mutate the schema. It's changed the schema. And at the end, the resulting schema after all of this mutation should match your desired destination schema. So this is, this is slightly different semantic. And that's what's guarantee that you will never lose the data, because so there is no way to remove some key from schema because you are mutating, and all operation keep these guarantees. So here is a set of guarantees. First of all, all operations are reversible. So, and you write only one program to do the back and forth transformation for the schema and to do the back and forth transformation for the data. So all the changes are reversible. You have a lot of verification and check that you are not shadowing data. You will never lose the information, and you may debug the step-by-step your program. And eventually, when you want to deploy it to production, you may compile it to very efficient the transformation program. That's This is an example how the Isomer may be applied to transform between the FIRE versions. Probably you've seen the FIRE application of the FIRE mapping language to transform between the versions, but it uses semantic building the destination from source. So that's force you to do the boilerplate copying all the elements from the source to the destination. And with this mutation semantic in Isomer, you can just put the couple of operations, like rename the keys. So you only describe what's changed. And so this is one operation in Isomer. So most of file version conversion will be done with one operation in Isomer. So nobody is thinking about this at least I haven't seen it in mapping language, but to keep the data, you can, for example, in a new resource, you have a new first class element to keep this data. So to make this transformation reversible, you probably have to introduce the extension for the old resource and try to put this data into this extension. So you see the special operation for the Isomer, which extract specific extension by the URL and put it under the key, like making it first class element. When it's run it forward, and to backward, it's taking this element and putting it into extension. Okay, and now I think we have just 5 minutes, and I will show you the demo. So it's, so here we have the source schema. And here we have the set of operations. The first operation say, find the address schema and rename the zip attribute to the postal code. And here you see the resulting schema. So you see, let me make it slightly small. So for example, you see that in address, instead of zip, we have a postal. So here we have a zip and address, zip. And let's rename keys, for example, in identifier, in original schema, for example, it's something from X12. So it was called code, but we want to call it the value. So we can run this transformation and it's transformed. I think it's even simpler to read not the resulting schema, but these data. These data are generated. So this data generated from the source schema. And this data is a result of forward transformation of the source schema to the destination. So we see that we rename the code to the value. Let's create the new schema to move the all name attributes, and let's push these attributes from the root of the entity to the name. So here you see it was at the first level was first name and last name, and here we have the name given family. It starts looking like fire, yes. So then we can move some fields from the extra and remove the extra. So that's the resulting schema. If resulting schema matches your desired schema, then you're done. If not, you will see something strange here. So, and that's how you can step by step start writing very complex. So we have a program with hundreds of such operations when we're trying to transform X12 EDI to the fire-like data structure. So, and I think, I have only 2 minutes for the questions about Isomer.
How many operation codes does Isomer have?
It's extensible. For now, we have a kind of dozen of operations. Okay. There are various some specialized stuff like working with extensions, mapping from collections to the keys. I don't know, even mapping from the enumerations of values to the new schemas. So if you can formulate the operation which will confirm to all the Isomer requirements, operation requirements, then you can introduce the new operations. It's a good mind exercise, but it's possible.
Is there a data? Sorry. Follow up is there a data structure that keeps a log of the operations, or is it just that every operation is always reversible by doing the opposite?
Yeah.
Like,
So
is there a history? Like, can I actually know in the stack kind of where I am?
yeah. From the developer side, so you can debug it. So I did this simple debugging here by commenting the rules. So you can, but you can imagine user interface when you can walk through the history of transformation and see this intermediate schemas and intermediate data. So this is going to be the part of the tooling for the Isomer. So, and yeah, it's completely debuggable. So you can walk through all of this stuff. And we did this because, yeah, it's going to be the hundreds of such transformation.
Okay, thank you very much, Nikolai, for your presentation. We've run out of time. If others still have questions, we will ask Nikolai if he can check the Q&A session of Wova. There's still one question left, so if you can in the Q&A, if you can have a look at that, Nikolai, afterwards, that would be nice. And then it's time to close this session. So again.
Yeah, thank you guys. Yeah, hope to see you in person, offline, eventually, when the pandemic will end. So you can find slides on GitHub.io. So DevDays US, blah, blah, blah. I don't know if we can publish this into some chat. I mean.
Yeah, you can do that. It would be nice. And
yeah, thank you guys. See you. Bye-bye. See you on Fireman, for example.
Thank you. Bye-bye.